Hi everyone, my name is Mzwakhe Didshe,
And I'm Realeboga Monare.
and our project is on Matabele end raids, and the focus is on optimizing termite control.
On the agenda is the background and the problem statement, and then we go into the data and exploratory data analysis, and then we go into detail on our methodology, and then results and discussions, then the deployment and conclusion. So just to give a background of our project, the global population is projected to reach 9.1 billion by 2050, with Africa expected to experience the highest growth rate. This anticipated population increase introduces the urgent need to implement sustainable strategies that will ensure long-term food security. Termites are known to pose a significant threat to food production through the damage they cause to crops and wooden infrastructures. To address this issue, synthetic chemicals have been used traditionally to control termite populations. The challenge that the synthetic chemicals pose basically serious environmental and health risks, and they also could lead to termites being resistant to the chemicals. It is therefore crucial to introduce sustainable, eco-friendly, and effective alternatives for termite control. Farmers have identified ants as important predators to basically address the termite issue they're facing in their farms. The importance of ants basically was recognized because ants are able to consume high termite quantities while still improving soil quality and nutrients. The Matabele ants are found in the sub-Saharan Africa and are notorious of their termite dietary preferences. In this study, we use machine learning. We couple machine learning with the ants and try to optimize the natural predatory nature of Matabele ants for termite control. We seek to identify key features that influence raid effectiveness, develop a multivariate predictive model, the XGBoost model, to predict raid success given various behavioral and environmental variables. And then we create an interface using Streamlit that allows users to simulate scenarios and observe the effect on raid success. We employed the Matabele and raid behavioral data from the Mpala Research Center in Kenya. The dataset originally included 18 variables, of which the below are the key variables we used in our study. The first explanatory variable is foraging distance, which we expect to have a negative relationship with the raid effectiveness. And then the number of ants in the raid, we expect to have a positive relationship to raid effectiveness. Humidity and temperature, so very low temperatures and very high temperatures, both we expecting to have negative effect on raid effectiveness. And then time of day, also going back to the temperature issue, we expect that raids would be more effective in the mornings where the temperatures are not too high. And then going into the month of the raid, we expect that rainy months will have a positive relationship with raid effectiveness. And this aligns with literature in that rainy seasons, we tend to see more termites, and therefore we'll have in average more termites carried per ant. We also look at the type of nest, and we expect that hidden nests should have a negative effect on raid effectiveness, as it should take a bit longer to basically raid those nests. And then termite species, we expect bigger species to have a negative effect on raid effectiveness. We define our success metric, we define success or rate success using 3 variables, which is rate duration, average number of termites carried per ant, number of ants injured or killed. And basically, we need the number of ants injured or killed to be as minimized as possible. And then the average number of termites carried per ant, we need it to be as high as possible. Then the rate duration should be as low as possible for us to say the raid was successful or it was an effective raid. We did exploratory data analysis from which we identified foraging distance and the number of ants in the raid as significant variables that could also be manipulated to improve Matabele ant raiding processes. I have attached the graphs, but we will speak more in detail of the interactive graphs that we have in our deployment slide. I'll take you through the methodology. We basically use 2 approaches to address or to answer our research questions. Firstly, we ran 3 univariate models. The first univariate model, we used average number of termites per ant as our Y variable. The second univariate model, we used the rate duration as our Y variable. And then the last and third univariate model, we used number of ants killed or injured as our Y variable. We basically we saw the need to run the 3 separate models to just understand how the explanatory variables will affect the Y variables individually. And then we use the 3 Y variables in one multivariate model, the XGBoost model, to basically allow for interdependence in the model. And then we used Streamlit to deploy the model. The model will basically predict the 3 variables given the different explanatory variables. Mzwakhe will take you through our results.
Okay, so our multivariate XGBoost regression model achieved an R-squared of 0.7, a root mean square error of 0.96, and a mean absolute error of 4.6. The R-squared of 0.7, we feel like it is acceptable, and it does explain quite a lot of the variance within our data. The top 5 features extracted from feature importance are time spent in the raid, duration of outward journey, number of ants in the raid, number of termites carried by ants, as well as the month in which the raid takes place. Also, some notable variables would be the foraging distance as well as the relative humidity. So we had to do a predictability, computationability, and stability check for the model that we have developed. And we used resampling with replacement to do the PCS check. So these 3 plots are the 3 target predictions for the 3 target variables of our model, which are the number of ants killed or injured, average number of termites per ant, as well as the total duration of the raid. The solid lines are the actual values. The dashed lines are the median predicted value, and the shaded region is the 5th to the 95th percentile of the predicted values across the 100 bootstrapped models. So this gives us a 90% perturbation for each predicted test sample. So for predictability, we can assess how well the median tracks the actual value. As you can see, for the number of ants killed or injured, the solid line doesn't track the dashed line very well, and our shaded region also doesn't track our solid line very well, which basically means for this target variable, the predictability isn't very good. For the other 2 target variables, the predictability is very good. And for the stability, the narrower the shaded region, the more stable our model is, because it shows there's very little variance in the predictions for the different bootstrap models. with a 90% perturbation. So again, our number of ants killed or injured has quite a wide shaded region, which means that particular target variable in terms of predictability and stability, it is not very good, but for the other two, it is. And for computationability, the model that we deployed was deployed on using standard computational resources. So our model does pass the PCS check. So we deployed our application on Streamlit, and we've made our plots interactive. You are able to filter the data based on the type of nest that the termites reside in. You are also able to adjust at which time the ants leave for the termite nest, and you are also able to adjust key variables that we extracted from our feature importance, such as your month, time that the ants leave the termite nest, relative humidity, and the number of ants in the raid, and so on. So by adjusting these variables, we create a data set that we feed into our XGB multivariate regression model, and it will give us a prediction. So in conclusion, Matabele ants are effective biological control agents to combat termite infestations. So we use this information and leverage machine learning to provide opportunities to optimize termite population control. We use our multivariate XGBoost regression model to extract important features in the termite raiding process, and this also provides insight for farmers and ecologists to simulate different scenarios for termite control strategies. Thank you for your time.